Okay, everyone, welcome to our advanced game dev workshop. Today we have pretty interesting topics to cover. Uh, so today we're gonna do some shader recap again. There is new faces, but I guess like all you guys been there. We're gonna cover ray marching, implement it as a shader, and then Sam gonna cover some Unity tools, which are gonna be useful for you. And then we also maybe gonna speak about the game jam.
Yeah.
Okay. Check in. Yeah, I guess you know who we are. We can skip this one. Yeah, as a reminder, this is our fifth workshop, and on the 10th of April, we're gonna have a game jam, which we all working hard to make the best game jam ever in Florida.
Yes. It is likely going to be during the summer. Just so you know. But it'll be like hybrid. It'll be online and offline. But for competing for prizes, at least one person on the team has to be in person.
Yeah. Okay. Yeah, the Notion page.
But you know, April might happen. April 10th and 11th might happen.
April might happen, but the looks of it,
No,
summer's a pretty nice.
it is not very hopeful.
I'm not, like, I'm realistic.
Did you realize?
You're not.
I have put this. You're doing the screen space also, right?
No, only Raymarch.
Only Remarch?
Yeah, which is like old content. I forgot to delete.
Okay. And then
Okay. Okay.
these are a list of topics that I'm just going to go over today. We're just going to go over mostly Unitask and do to me, and then the rest just leave for self-exploration. But just go over them briefly and explain what they are, how they're used, and how it helps you.
Okay. Advanced game dev. All right. Welcome to the game dev. You came to advanced game dev, and you probably want to land into industry. Like, does anyone want to have a job like connected to game dev?
No.
Let's go.
Yes.
Let's go. So, quick reality check. Market is rough right now. It's kind of too many people and not so many companies. As you know, many teams who develop games become close, close more and more. Like one of the safest islands was the Xbox, I guess, but since the retirement of Phil Spencer, it's not gonna be as good anymore, I guess. So being good is not enough anymore. You need to stand out. So how can you stand out, actually? By not doing the same Unity tutorials, by not doing another FPS clone. My suggestion, you can stand out with visuals. Like you can do some tech that looks hard, stuff people don't understand at the first glance. Because from my experience, like if you're just a general game dev developer, but you have like at least a little bit of the shader on your resume, like it make like so much difference. So yeah, easy win is a shader. You can add shaders to your project. It instantly looks advanced because anything lower level usually ignored by people, and people are afraid of it so much. Why? Because yeah, GPU is scary for most of the people. Math is avoided, but result looks insane. Yeah, and as a result, you get like low competition and high impact. So one of the effects in shaders, one of the coolest effects you can do, called ray marching. That's not something really new. This thing was discovered like in 80s by some researchers and professors, but it became quite popularized in recent 10 years. What is it? It's actually a way for us to render something without relying on polygons. So as you may assume, like if we working with some game engine or like any kind of rendering space, any of the mesh we doing, like any of the object could be like your character, your map, tiles, anything, is always just a shape made of bunch of triangles. More triangles, it become like look more realistic, more smoother, but at the same time it comes with opportunity cost at more computational cycles. Ray marching is kind of a way to get infinite quality because like you're not relying on vertices anymore. More on that later. So yeah, it looks complex, feels like magic. It's actually simple. I will try to explain it as simple as possible. And I bet you stand already like in some projects like CS2 because when they released like the CS2, they implemented a new small grenade. If you play it looks awesome. Like actually, it can fill the spaces, and usually the remarching come to the place where you wanna render something that is hard to define with vertices. So some clouds, some smoke, maybe water, like actually anything. So yeah. Quick reminder about the shaders. Shader is our way to define how something should be drawn on the screen. It's like a bunch of instructions to your GPU. Think of your screen as a million of tiny pixels. Does anyone don't know what pixel is? Okay, like your screen is usually made of a bunch of squares which have like three color components, and mix of them define the color on your screen. And the instructions we're gonna do in shaders is actually made to output some colors we wanna like have on the screen. Yeah, and so far we covered two types of shaders. It's like the ground basic is vertex shader, which decides where things are, move points. And the fragment shader decides how things should look like color, light, effect, etc. So as we're not relying on any vertices, ray marching take place in shader and fragment shader. All right. So let's move on. Today I decided to do something different. We're not gonna use Unity shaders. We're gonna introduce something new called shader toy. I guess many of you familiar with GitHub, right? So this is like a place where you can hold many of your projects, find the others' projects. So shader toy is kind of the same thing, but for the shaders. So if you go to shadertoy.com, you can create account, but it doesn't really necessary. So this is like the goal for any game developer, because this is not only a repository for you, but it's also like a great community for any shader developer. So I mean, the concept is pretty like simple. Like there's a bunch of people who sharing their works, and it's open source. So for example, you can come to any shader effect, which they shared on the website, and instantly like see how it was done, like all the code was used there, and try to implement to your games. But it also a great space for yes.
What language was that? The shader?
Yeah, I will cover it. Yeah. So it also allow you to like write the shaders right there, so you don't need any kind of environment, as we needed before. Like we used Unity and the shader graph. So shaders could be written with the blueprints, as we did in Unity, but it also could be made with the code. And usually there's two main languages to write shaders. HLSL, which stands to High Level Graphic Language. And this is the one that's used in Unity, And if we go to APIs that used in Vulkan and DirectX, that's the one that was mainly popularized by Microsoft and was implemented by Microsoft, and in recent years by NVIDIA too. But for the learning purposes, today we're gonna use another syntax that was introduced a bit before HLSL, which is called JLSL. Syntax is kind of the same. It's like all the C style. I mean, if you ever program in C, C++, Java, C#, you're kind of familiar with the syntax. It's straightforward. The only difference is could be like, for example, in JLSL you like write vector free like this, but in HLSL it could be float free or something. Yeah. So today we're gonna make our shader in this environment. So does anyone cannot open this website? Can I have thumbs up if you can open? Right. So, okay. Implementation. First of all, what you see right there is a little bit coded pipeline, because usually when we work in Unity with shaders, we have some objects which we want to pass to our shader, like to have some effects as we was doing with the trees, with the water in our game. But today we're not having like any 3D objects. Imagine that all objects you're working on is the full screen. So in this case, we can just ignore the fragment part of the shader, the vertex part of the shader, and works only with the color. So when you come to the shader toy, you usually have a sample code. I will explain what it stands for. Okay, first of all, as many of the C languages, the shader language HLSL and JLSL usually have the main function. This is the one where you need to output something. Like in C++ and C, it's supposed to be return 0 if you used to code on those languages. There, we need to return the color. So as you can see, we can do this by giving the value to the front color variable, which is a type of vector with 4 components, where first 3 is red, green, and blue channels, and the last one is transparency. Well, when you just come to the shader toy, it make like small animation code. Let's do step by step. So first of all, we're doing a new variable called UV of type vector2. Because we have a flat screen, we need a vector with 2 components, x and y. And we define like the coordinate space. Yes?
Which shader is this?
What do you mean?
Like, where did you find it?
Oh, okay. When you come to website, you can go to the right top corner and click new. So this is like the space where you can create a shader. It's like the sample one. Yeah. So right now, first of all, we defined the UV is like the coordinate space for us. We're gonna use later. It's made by taking the frag coordinates. That's the one that we passes from the vertex shader, and the one we're using to define like where I have like the bottom left corner and top right corner. And in this space, we divided by our resolution, x and y. So we have like a full screen coordinate space. So everything we're gonna do is gonna be like within this flat image. The next part is some example how you can play with the color. So let's empty the variable vector-free color. Just delete the stuff there. And let's create a new value. So yeah, the color is the variable that gonna contain the information for our pixels in terms of red, green, and blue channels. So if you want to like give some value to vector-free color, we can make a casting to our values. So we need to write back free, then open the brackets and put the values of the color we want. For example, if you want just red color, it's supposed to be 1 and then 0, 0 in other two channels. And one important thing is JLSL cannot cast values to each other by default, like Python does and many high-level languages. So that's why you need to be so explicit in what you're writing. So as you can see, we're not just writing back free color works to equals to 100 because it's gonna break. We're gonna specify that this one is vector free, and in the brackets we specify that this is 1 point because JLSL works with the float values. And if we're gonna click the compile, wait, okay, we have some problem right there. Oh, I can see because I didn't put the dot right there. So if we're gonna compile, we're just gonna get the full color on the screen. Did you get this thing? Or, yeah, it's supposed to be decimals because we need to explicitly tell this is the float. And you forgot to put
Oh, semicolon.
yeah, semicolon.
Oh,
Because as any C language, you need to end the line with semicolon. Alright. And this is like the whole concept with fragment shaders. That's like the ground from which we're gonna work around with the ray marching. So there's like bunch of stuff you can do. For example, you can pass time instead of some of the colors. For example, let's change the green channel to time. To do so, you need to change it to iTime. This is the variable that passed by default to your shader. And if you compile, it's gonna change the color over time. But because time right now is like 5-10 seconds, we need to like start again. If you click on this button, you like restart your shader. So it's going again. As you can see, it's changing like color of the screen by time. Okay, so this is pretty much all you need to know about the fragment shader. Everything else is just techniques that allow you to play around this simple concept. So let's back to the presentation. Okay, ray marching. So imagine that you are the camera and you shoot a ray from the pixel. So for example, you stand in the room and you're blind. You have no idea like what's around. You cannot see like the chair, the table. You have to rely by throwing a ray from the room until it hits something. But this is not really optimized. For example, how do you know how much should you throw the ray so it's gonna hit something? Because it could go more than some object stand right there, or maybe not enough to hit something. So ray marching is kind of a way to mathematically be sure you're gonna hit something. The idea is straightforward. So for example, imagine if we would be able to ask the space what is the closest object we have so far. For example, I'm standing right here and I'm asking the space, like what I have around. And and it returns that I have a chair right here. So it means the distance between me and chair could be safe to move in any direction. For example, I moved into direction on the chair distance, and I'm asking again, and it tells me that like the table right there is the safe distance. I'm taking the same distance, and I can walk again. I'm asking like again, what is around me, and I'm constantly doing this more and more until I'm gonna hit something. I'm gonna hit the table, and the distance between me and table gonna be so small that I can understand, okay, I hit something, I can like finish iterating from it and return something. So this is the key idea. And imagine this is the way of only one of the rays we have, but we're gonna have so much more of them. How we can define the ray? Well, pretty straightforward, because again, the screen is a little bit different from the eye view. So we need to define something called frustum. This is like the space when you can see something. So for example, we're gonna define some point in the space, which is gonna be our 0 in the space. And then we're gonna define some space between this point and the screen. So by defining how far the screen is, we're gonna define the field of view, which is usually implemented in some games you play, and you can change this one in the settings. And then each pixel on the screen is going to be used as our direction for the ray. So for example, if we have a default Full HD screen resolution, how many rays do you think we're gonna throw? Any idea? So to define how many rays we're gonna throw, we're gonna have to like just multiply our resolution 1920 to 180, and this is how many rays we're gonna throw. And you can imagine how slow it could be if you would do this one on the CPU, because in this way you're gonna iterate from each of the pixels like linearly. But again, in the GPU, everything happens in parallel. That's why we benefit from that. Okay. Any questions on this point? Okay. But the question right now is how we can actually define, some depth and perspective on the screen. So we're not gonna do any lighting so far because it's gonna be too complex. Instead, we're gonna do a simple trick. We're gonna use the distance that our ray is gonna pass through iterations as a color. In this case, the closer objects gonna be lighter and the further gonna be darker. Because, for example, for example, like distance is 0.1, we're gonna use it as a color. It's gonna be black, and if like ray exceeds 1.0, 2.0, it's gonna be brighter and more closer to the white. Okay. So how it's supposed to look in the shader code? If you go to the Notion page, you can open the what is ray marching section. So again, this is all content I just covered, but maybe a bit better because you would be able to read on your own. And if we go to implementation, there's like a bunch of code we're gonna copy to our shader. Can I have thumbs up if you open the Notion? Okay. So first of all, to being able to work with some space in our shader, we need to define the UV coordinate again, as we did in this shader. But right now, our UV space is the full screen. But for the ray marching, we want to do something else. We want to move it to the right and to the top. So this corner becomes middle of the screen. So to do so, you have to copy this line of code and just replace it with the default UV coordinates and compile. So if you want to actually see what it means in terms of the shader logic, we can do like that. Okay, as you can see right now, like the middle x coordinates is centered. So it means if it goes to the right, it's going to be the positive value, and if it goes to the left, it's going to be negative value. Negative value in terms of color is just black. So that's why I have a black screen. And the same happens if we're gonna take the white component of the UV. As you can see, the 0 is in the center, and if we're going to bottom, it's going to be negative value, and if we're going to top, it's going to be positive. All right. The next thing, we need to define the ray origin and ray direction. As I told you before, the ray origin is going to be the actual point from which we're starting the ray casting. And the ray direction is going to be the pixels on our screen. So if we're going to write ray direction to be a UV, it's actually going to take the coordinates that related to the screen space. So we're just going to take these two lines of code and put them right here. Okay. So the next thing is we need to implement the ray marching. And as you remember, when we're trying to ray march something, we need to iterate from it until we're gonna hit something. How we define if we're gonna hit something? The value of the distance becomes so small, it becomes unreasonable for us to calculate it to continue calculating this one. So to define the appropriate calculation and optimize it a little bit, we need to do two macros. Macros is kind of a constant that we can define at the top of our file. So it could be like pi equals 3.1.14. Or for example, in our case, we can define max distance. So if you want to write some macros, you need to use the keyword define and the name of the variable. And then you have to put the value you want to give to some constant. So we're gonna need three macros. Max steps, which is gonna be 100. Max distance, which is gonna be 102, and the surface distance, which is gonna be the small enough distance that it's unreasonable for us to continue calculating the ray margin. Can I have thumbs up if you finish this one? Okay. So the next step for us is gonna be implementing the ray marching function. As in any C language, you can implement function by typing the type it's supposed to return in result. In our case, it's gonna be float and the name of the function. In our case, it's gonna be ray march. And you leave brackets as some kind of input you want to provide to your function. Then you open the curly brackets like that. And inside you're gonna write the actual functionality of the function you want to implement. So if you will scroll down to the full shader code, we can just copy this ray march function and place it right here. Okay, and press save. So what we do in this function? First of all, we define the distance. When we just start the iteration, the distance is supposed to be 0 because we didn't go like any distance from the array origin. And then we use the for loop where we're iterating from 0 to the max steps we defined before. So while we're doing that, we define the vector 3 e, which is gonna be our current coordinate in the space. For example, I move like this distance from table. For example, my coordinates is like 1, 2, 0. And what I'm do is put this one as my p variable. Then we want to like ask the environment how far like any closest objects is from me. To do so, we define a float called distance to the closest object, and to take the actual distance from something, we pass our current coordinates to a function called map, which we're gonna cover later. But for right now, just think about it like magic function that gives us the closest object in the whole world. And then we have 2 breakpoints. For example, if our distance is too small, that it's not reasonable to calculate, we're gonna break from the loop. And then if our array is going too far away, we're also gonna break. If none of these conditions happens, we just add the distance to the closest object to our first distance variable, which is defined like the safe distance for us to travel. And then we just return the actual distance as the output of the remarching variable. So if we go back to our main function, we're gonna introduce some code to start using the function we just implemented. Again, you can just go back to the Notion page and copy the code we have right there. So again, yes, we have our ray origin, we have ray direction, which is defined by the pixels on our screen, and then we taking the actual distance our ray traveled from the ray march function. And then we have to initialize the color variable, which we can then gonna change based on how long our ray traveled. So okay, one only thing left is actually implement this magic map function. And to do so, we need to cover one last concept for the ray marching called sign distance field. So if you look into this diagram again, you may notice there's like something weird happening around the sphere. So because we're not relying on the vertices, we need another way to define some geometry. And we can do this by using math. So sign distance field is actually a functions that mathematically explain like any geometry. For example, if you look into this diagram, as you can see, right there we have a combination of different sign distance functions, which is you're not supposed to like implement them from scratch. There's like some resources where you can find these functions. And if you go to the Notion again, if you go to the SDF, I put it two links to the website of really good programmer called Nikita. This is a developer from Sweden. He used to work in Pixar to some movies I bet you watched. And right now he's working in Photoshop on some of the tools they provide in the software. So like this is the guy who popularized the ray marching as it like right now. If you go to his website, he provide like all of his research, which you can use right away. He explained different mathematical equations which you can use to define like different kind of shapes. So kind of hello world program from the ray marching is actually our aim to render the sphere. The sphere have like the simplest math function. It's just the length of the vector we're passing to the function minus the radius of the sphere. So let's implement it into our shader. We can create new function called map of type float. In which we're gonna return the global distance, like in the whole coordinate space. And inside this function, we're gonna implement other sign distance fields together, like combine them to make the actual environment we want to implement in our world. So let's implement one more function for actual sphere sign distance field and put it right here. So our map function is gonna take as input the vector 3, because we need to give some world space coordinates to explain our map function where we currently exist in the world. Vector 3p. And then inside the map function, we're gonna just return the length. But since we only have like sphere in the whole world, we can just return the SD sphere. And as you can see, our function for sign distance field of sphere need the p and the radius of the sphere you want. So let's give it a p vector, and the radius, it could be like 0.5, for example. And if you compile, yeah, here it is. You just make your first ray marching shader. Can I have thumbs up if you did this one? Guys, did that help? If you go to the Notion page.
We're not too technical.
No problem. Okay. And at this point, you can start experimenting with the shapes you want to have on the screen. For example, you don't want to have a sphere. You can take something else. You can, if you go to the Notion and open another page, this one is explicitly shows the 3D SDFs. For example, let's try to add box in our environment. What we're gonna do, we just copy this code and put on top of our shader right here. So on this point, we can start calling this one from the map function. So instead of returning the sphere, let's return the assign distance field of the box. So again, as input, it needs the p vector, which is just a position in the space, and also it needs the vector 3, which is gonna be defined just the shape of the box. Let's put it to 1, 1, 1, and compile. Okay, yeah, here it is. Let's change it to be a little bit smaller, like 0.2. Okay. Nice, way better. But you may ask, how could we introduce several objects in the same space? Well, again, as the main idea of the map function is to tell the distance. If we have several objects, we want to check which one is the closest one. So let's change our map variable a little bit. Let's introduce 2 new vectors. It's gonna be vector 3. Let's do b chord, which is gonna be, for example, b plus some vector 3. Okay. And then instead of just passing, yes.
Where we should find the SD buttons?
Okay, if you go to the Notion page, I provided the link to the website of Ray Marching developer right there at the SDF. If you open the second link, you will go to his website where you can find like list of all functions you need for Ray Marching. Yeah. So yeah. So instead of passing just a p vector to our box SDF, we're gonna introduce its own coordinates, which we then can like change by offsetting it a little bit. So instead of giving it p vector, let's give it p chord. Okay. Oh. My bad. I misspelled the name of the vector. Okay. Supposed to be working. And right now we can change the values of the vector we add to the p coordinates to offset the box on the screen. For example, let's put 1 as x coordinate, and as you can see, it's moving to the left. And if we, for example, pass not some constant value, but for example, sinus of time, we can have some animation on the screen. So let's change it to sine of I time. Yeah, and by doing so, as you can see, our box start just moving around. Again, it could be not time, it could be the input. Because on the ShaderPlay website, you can actually introduce the input from your keyboard, and some of the guys making like real games just inside of Shader. So yeah, again, it's just like a huge sphere that could be very interesting if when you go deeper and deeper. Okay, but how can we render like several things? For example, we want not only box to be rendered, but we also want a sphere. So let's first introduce another vector, which is gonna be defined as coordinates of the sphere. We're gonna name it something like s-chord, and let's make it equal p plus some vector 3, which is gonna have coordinates of 0, 0, 0. Okay. So now we can use these coordinates, but right now our function, our map function returning only distance of the box. To make it returning like both of the things, we need to use OpenGL function called mean. This one allows you to take the minimum distance from two lengths. So if we're gonna put mean of SD box and then mean of SD sphere, and we're gonna pass its own coordinates for the sphere SDF, and then gonna give a radius of 0.2 and compile. As you can see, we have both a cube and a sphere. Yes? Yeah. The code?
Yeah.
Okay. But we're not forced to use the appropriate ray marching. We can change the mean value to max value. So instead of taking the distance to the closest object, we're gonna take the distance to the furthest object. And this is gonna make us some kind of interesting effect. As you can see, right now, instead of giving a sum of two objects, they cancel each other. For example, if you will change radius of the sphere to something bigger, for example, let's give it radius of 1.2. Yeah. No, wait. Okay, let's leave a sphere of the same radius. Let's change the size of the box instead. Let's increment the size of the box by 1. Oh wait. Okay. That's not something I expected. Okay, what's gonna be the problem? Okay, if you will open the website I provided, it also have section about the different operations you can do with the shapes inside of your ray marching. So, for example, if you want to sum them together, you can use mean. But if you wanna, for example, subtract one shape from another, you have to use. Oh, okay, that's the problem. We need to use negative value of the SDF. Okay, we'll go back to our shader. We need to change the SD sign to be negative. Okay. All right. Yeah. as you can see, right now, the cube is actually feel the sphere when it pass inside of it. And there's like many other ways you can play around with it. Just like on your when you have free time, just open the website and check the stuff. But just one more thing I want to cover. So let's roll back to just having a sphere. Let's delete SD box and just return the sign distance field of the sphere. Okay, to keep it being right there. One more interesting function I want to cover called the fract function, and what it allows to do is make multiple iterations of our coordinate spaces. So let's do something cool. We're gonna call the p vector inside our map function, and we're gonna set it equal to fract of p. And then we're gonna compile it again. So because we have a too big radius of the sphere, we need to change it a little bit to 0.2. Okay, and then we're gonna subtract 0.2 from our fract of the p, and that's gonna give us something really interesting. Can I have thumbs up if you get it? Okay. So the problem is because right now your camera is like inside of sphere. To do so, we need to subtract it. Try to decrease the size of the radius. Yeah. Yeah. Okay.
That was the solution. Thank you.
Okay. Nice. Okay. Here's the problem. You subtracted 0.2. Because of that, illusions kind of breaks because you're not centered, but you like offset not enough. You change it to 0.2 and compile again. 0.2. Yeah, you have this problem. But if you wanna roll back to 0.5, here. Yeah.
Oh, okay.
Okay. And you can make like some crazy animations by doing that. For example, we can ask our camera to fly through this space. If we go to the main image function, we can change our ray origin. So it's not a static point in the space, but instead we can give as one of the coordinates the time. So if we're gonna change the z component of the vector and compile, yeah, our camera start flying through the space. I mean, this is so cool. I like it.
That's pretty.
Yeah. Can I have thumbs up? Yeah. And again, you're not only limited to work with camera. You can change the p vector. For example, ask it to move around. Okay. What we can do is also work with the coloring. For example, yeah, right now we're just using the distance as the color for our shape, but because we're not defining like any color palette or anything like that, it's just using the same values for all of the channels. So if I have like the same value for R green and red, green, and blue channels, it's gonna be something gray or white. So we can change it by introducing the coloring of our object. I hope I covered it there. Maybe not. Okay. One more thing. Okay, I want to cover. As you can see in this portion of the function, when we check if we exceed the maximum distance, we actually can change the rendering distance of our remarching. So this function, which allowing us to color the objects, could be modified a little bit. If you will make the value smaller, it's gonna give you the greater distance. For example, if you change 0.2 from 0.2 to 0.1 and compile it again, you're gonna have a greater rendering distance, and could be either smaller, something like 0.2. Wait, wait. Yeah, like that. Okay. All right. One more thing I want to cover before finish is there's many like fun sign distance fields you can find on the internet. One of the things I like is do you know do you familiar with the complex numbers? You know what is fractals? Okay, we can do some fractals there. If you go back to the Notion, I found a really beautiful SDF for the Mandelbrot. It's kind of 3D version of Mandelbrot set. If you familiar with fractals, you probably heard about it. If we just put this one right there, yeah, we can replace our sphere with the model bulb. Okay. Let's do so. Okay, but we hit into problem because our SDF is too big. Okay, how we can work around it? We can change some of the input we're passing to the SDF. I assume this one is gonna fix something. Wait. This is what I like about the shaders. Even if you like face into some problem, you can just like try it out. Like put something random. Maybe you're gonna like give it something cool, and you can use it actually. There's no bugs. It's all features for you as a game developer. Okay. I don't really know how to change it right now. What I'm gonna do instead, we're gonna roll back again to the not having the repetitive function. We're gonna delete this p equals fract and try to compile again. And I think we're still hitting something. Oh, I got what is the problem. We need to replace our time again to being -3, so we can actually see the object. Okay, we still don't see it. Probably we're too close to it. Let's go back. All right. Okay. I don't know, like, if your GPU is good enough to handle it, because like this is fractals, so many operations happens. But this is the fractal right there. I bet you've seen it somewhere on the internet. It's usually used for some wallpapers. Yeah. So if you will like do some shading or maybe color it good, it's gonna look like that. Yeah, but this is the same thing we have there. And again, this is the advantage of ray marching. No way you can render something like that with polygons. I mean, it's too hard. So yeah, this is kind of all I had for today. Let me double check the presentation. Where is it? Yeah, okay.
Thank you, Nikita. Do you have the project? Is it?
Yeah.
Like the latest one, the last one that we finished off with?
I hope so. Okay. Oh, I need to close the shader. It's so heavy. Okay. Do you like the last project? Because probably I have one from the workshop 3, I guess. Probably.
Like the last one, yeah. I can record on my side and just
Okay.
resume.
Okay, it's fine.
And then we can merge them.